All right, everyone. Good afternoon. I hope at least some people are familiar with South Park, or this joke was probably going to completely fall flat. But there's a episode of South Park called The Underpants Gnomes, where there's a bunch of gnomes who go around stealing people's underwear. And this is something similar to what they present as their business plan. So their business plan is steal underpants, ? Profit. So the idea of this is it was a satire on Silicon Valley. All right, okay, all we need to do is, we don't necessarily need to know how we're going to convert what we're doing into value. We just need to kind of capture a whole bunch of users or a whole bunch of attention. Then whatever that ? is will take care of itself, and then we'll finally get to profit. So I guess as one of the industry people here at this conference, I guess it's my role to, in the same way as a luminary professor might ask you, well, how does this advance type theory? Well, it's my job to ask, well, how will this kind of discipline profit you? And so in particular, I want to talk about computational musicology. So what is computational musicology? So there's a definition I lifted from quite a cool paper, which talks about computational musicology as the study of music by means of computer modeling and simulation. So I think this is an adequate definition, but I must admit, when I read this paper, the fact that they use the word broadly as a description of this was something that I didn't quite agree with. This actually feels like quite a narrow definition, and in fact, if you look at the way that the folks in this paper talk about what they're doing, they have kind of some anxiety that what they're doing as computational musicologists doesn't really have a natural object. So they talk about, well, chemists have molecules and atoms out there and they can study them, they can do scientific experiments, but we don't have that. How are we going to do proper science? And they even actually talk about how to make their paper into proper science, and that's how they end up arriving at the conclusion that they should use an artificial life approach so they can kind of simulate a bunch of music and then study it. But I want to question whether that kind of modeling and simulation approach to what computational thinking can bring to music, whether that's the only way to think about things. So there's a very famous lecture/essay by C.P. Snow about the two cultures. So basically this is where C.P. Snow identified that in academia there's two very different ways of thinking about things, two very different schools of thought. There's the humanities and there's the sciences. So this isn't something that's always existed, it's something that throughout the 20th century has developed. And, they have their own methods, their own conferences, their own way of presenting results, their own notion of what rigor is. I think that when it comes to computational musicology, we're a little bit stuck, because if we want to accept this dichotomy of the scientific way of looking at things and the humanities way of looking at things, then what should something that is both computers, which gets associated with the scientific side of things, and music, which gets associated with the humanities side of things? So we've got, how should it behave? How should it conduct itself? What kind of, should you write essays or should you write papers? How should you put things together? So Marvin Minsky, who's very famous as a computer scientist, wrote quite an interesting essay called Music, Mind and Meaning. And I call it an essay deliberately because it wasn't really a paper. He didn't really operate in the mode of a paper. He didn't have results or theorems. He didn't kind of state specific outcomes. He made a lot of associative claims and generated a lot of ideas. And he observed the same thing that I saw in that previous paper that I cited, which is that we, meaning folks like himself who are into computer science and also music, we would like to study Mozart's music the way scientists analyze the spectrum of a distant star. So there's kind of two elements to that. One is the idea that there is a natural phenomenon out there that you don't necessarily have to appreciate cultural context to understand. The other thing is that there's no dialogue with a distant star, right? It may not even exist anymore. It may, it's kind of a one-way, you're an observer of an object. There's no kind of dialogue there, which there is in humanities practice, right? So a literary critic will write about writing, and that will be something that will actually influence the writing itself. So there's actually a feedback loop between the act of analysis and the act of criticism and the creative act itself. And that's not true if you purely think of music as a natural phenomenon. If you think of it that way, it doesn't really give you a way of thinking about musical practice itself.
The fact Mozart is dead helps to...
Well, Mozart is dead, so I guess you could say that what's left of Mozart's repertoire does represent a kind of a natural phenomenon that we can go through. True, but there will hopefully be maybe not future Mozarts, as he's probably a singular genius, but hopefully there'll be future people that, if we really do our jobs well and analyse music well, that might take some inspiration from what we do. So Minsky kind of slightly satirises the idea of applying a purely scientific approach to music. So imagine formulating laws for television screenplays, taking them for a natural phenomenon uninfluenced by custom or constraint of commerce. Right? So it's not to say that you couldn't come up with a very interesting explanation of music that is kind of purely structural or mathematical, etc. But what he's pointing out is that there's a lot more to it as well. So in the paper and in the talk today, I'm going to play a lot more with maybe a more literary way of applying computational thinking to music, and also cite specific artworks that artists, whether they're writers or musicians, have used computational thinking to inspire them, and they've incorporated it into how their works function. So I'd like to start with Bach, and I've done a lot of work on modelling Bach with programming myself, but the first thing I want to start with is actually a different kind of string, so a string of characters in programming. So the basic idea of the talk that I want to start with and then expand out into how it applies to various creative works is that of Kolmogorov complexity. So if you look at this, the line under the cursor there, sorry, that's a bad highlight, it's a billion Gs, right? So that expression, or the one here, identifies a string that's a billion Gs long, right? So that's kind of large. I did some rough back of the envelope calculations, and that's like 5 times as big as the iTunes library. So that's quite a, that expression there represents more data than what you might practically say is the sum total of the music that we have available to us. But it's obviously not complex. So there's some kind of difference between the raw amount of data and the actual inherent complexity of it. So if I take the first 10,000 Gs, well, there's a lot there. Right? So Kolmogorov complexity is a definition for inherent complexity of something. So it says that you can measure how much inherent complexity a piece of data has by the shortest possible program that can produce that data. So there is a lot of subtlety about, well, what programming language are you going to measure this for, and what are the primitives in your programming language, etc. But I'm going to just kind of sweep that under the carpet for now and just kind of assume that by using reasonably clean code, we're going to get to that. So I've got a macro here, enclosure, that takes an expression and calculates the length of it as a description. So the length of the program that calculates it. So all this macro does is it takes the unevaluated expression, because we have macro time in closure, prints it as a string, and then counts the length. So trivial function. To calculate the result length, I do something very similar, but it's an ordinary function. So you can see it says defen there rather than def macro. So it's the value that's passed to it, well, it's strict, so it's already been evaluated before the function gets it, turns that into a string and counts it. So if we look at, maybe I can just slightly change the size here. So if we look at this unit test, the fact is that the description length of repeating 65 Gs is 13. So that's the length of the string you'd need to do that. The result length, though, is 131. So what you could say is that expression, repeat 65G, has quite a considerable explanatory power. So the ratio between the actual expanded result, the compression ratio, and the actual original expression could represent how much explanatory power that expression has for that particular piece of data. So the more structure that the expression understands about the resulting data it generates, the shorter the program. As it happens, this gives us a definition for what random means. So if you have a piece of data that there is no possible program that's shorter than just writing out the data longhand, then basically it's uncompressible, it's random. And this is undecidable in the general case. I won't go into the proof, but there's basically a fairly simple proof by contradiction that showed that if you could figure out the inherent Kolmogorov complexity of a piece of data, then you would generate a contradiction. But this is quite a useful thing because effectively it shows that compression and understanding are effectively the same phenomenon, right? So to compress something, you have to understand how it's structured. To understand how it's structured, your understanding can be viewed as a compression of a piece of data.
Excuse me, but
Oh, yeah.
Taking an expression,
Yeah.
taking a language that, a string, taking
Yeah.
a language that generates
Yeah.
strings, you can enumerate the
Right.
language one, but the program one
Yep.
by one.
Yep.
And so it's decidable.
So,
You then take the least, the smallest. You stop when your program is bigger than the input string.
No, but the programs themselves don't tell.
there is a proof, and perhaps I've explained the context of it a little bit badly, but effectively, for one expression, you can figure it out, but for a particular piece of data, it's you can't necessarily figure out the shortest way to do it, but maybe you can catch up afterwards. And there's actually kind of a way that it becomes irrelevant what the best possible way to compress a piece of data is, because what David Meredith, who does computational musicology, has been working on is the idea that you can compare the quality of two analyses of the same data by how long they are, basically. So if you are able to explain a piece of music using a short, concise program, that embodies a better analysis than if you have to notate it in a really kind of longhand form. So basically kind of like refactoring as embodying understanding. So the way he started out doing it was looking for geometric regularities in classical music. Like this is a piece of Bach, I think. So by spotting the repeated patterns, he's able to compress it to just using a program to say, well, take this core pattern and project it in these places in the music. So he says, I will propose that a musical analysis can be modeled as an algorithm or computer program, and the length of this algorithmic representation can be used as an indication of the quality of the analysis. So it's a way of applying kind of computational methods to different ways of analysing the same piece of music, is the idea. And so a practical example of that might be, well, a tune that I played to you earlier, which is Row, Row, Row Your Boat. So this is a program that, or the expression that emits Row, Row, Row Your Boat. I won't necessarily bother playing it to you because I've already played it to you a few times today. But effectively, because that program itself is much shorter than the output representation, that is by David Meredith's methodology, you can argue that that program embodies an understanding of the structure of Row, Row, Row Your Boat. In particular, this line here. So, if you ever heard of the concept of a round or a canon, so that the idea is you play the tune once, and then you play the tune again with a functional transformation. So it's basically a functional programming concept. You need a higher order so simple 4 is canon is a higher order function that takes a transformation and plays the melody twice, once transformed and once on its own. So actually I think I will play it for you. So what you should hear is the melody start and then the same melody played after a delay of 4 beats. That's why it's a simple canon. The second one starts. So if I'd had to write Row, Row, Row Your Boat without the concept of a canon, it would have been a much longer program. So you could say that by exploiting that structure of the music, that analysis has some understanding of it. And using the same methodologies earlier on, if we compare the length of the program to the length of the output, we definitely get a very high compression ratio. So this gives us the possibility of starting to use the length of programs that generate music to make judgments about how complex a piece of music is. So I don't mean that in terms of a value judgment. I don't mean more complex is better. In fact, in some ways, maybe less complex can be better. So minimal music, or minimalism, tends to be actually, if you analyse it, computationally minimal. So the amount of program you need to emit a piece of minimalist music, like for example, Steve Reich's clapping music, is actually not very big. So you can, by using that computational way of structuring it, you can actually substantiate the claim that it is minimal. It's conceptually minimal. There's not much thought or calculation that comes in. So clapping music is defined as, there's a pattern called the African bell pattern, which is defined by this rhythm here. So the way that the structure of the music works is that pattern is played forever with the part of clap 1. And then it also has a canon structure, but the accompanying transformation, basically every 32 beats, has an extra beat chucked in. So Steve Reich had this technique of phasing. So he had 2 parts that start in sync, and then over time, 1 part slips out of sync. So he did this in all sorts of different ways, but clapping music is one example. So this piece of music, if executed, will play clapping music. All right, so they're in sync. And they're out of sync there. I'm wondering whether I've got stereo on. Let me just quickly go to how I'm instrumenting these things and get rid of the stereo effect, because I think we're not getting a full stereo. So I'll just try playing again. We should hear both drums this time. Right. We should hear them separate about now. Right, so that you could say that's complex, but actually from an information theoretic point of view, it's not very complex at all. The structure of it is very simple, but it's just that to your ways of hearing rhythms, it's kind of hard for you to assimilate it. So it's a difficult rhythm to get your head around, but it's not the same thing as saying it's complex. And of course, it's minimal. So if we apply the concept of the description length, we can see it's only 228. But if we take the result length of, I don't know why I chose that particular, but the first 216 seconds, you can see it's almost 100,000. So it's a very compressible piece of music because it's very highly structured, and very highly structured is the same thing as saying very little inherent complexity. So there's another piece of art that I want to cite, other than kind of music like Steve Reich, which is a book called The Library of Babel by Borges, or a story called The Library of Babel. This is kind of a really arresting short story where effectively the hapless narrator is within this vast library of hexagonal rooms, and each room is filled with bookshelves. And if you go to any of these bookshelves and you open it up, you see, well, sometimes, most of the time, you'd see gibberish. Other times you'll see a book that is, the first half of Wuthering Heights and then gibberish. And so basically the concept is that every possible book of 400 pages is present somewhere on these shelves. So it embodies all possible books. One of the paradoxes is that on the shelves should actually include a book with the Library of Babel itself in it, or also the Library of Babel with the ending changed, or the Library of Babel with every E turned into an O. So the idea is it's this kind of combinatorial concept. And this, I think, is clearly playing with ideas about discovery versus authorship, because Shakespeare's works are inside this library. The Bible is inside this library. Every kind of creative work is already present inside this library. So it's kind of suggesting that, well, when we create something, are we really inventing something, or are we just performing some kind of search on a very large search space?
Any idea of what's the size of the building containing this library with regular printing?
I'm sure you could figure it out, because it would be finite, because the books are only a certain width. Yeah.
Won't it at least cover the planet Earth and the solar system?
I don't think it's. Oh, that's an interesting point. I don't know. Maybe that could be a homework.
There is a big exponential there.
There is, and there's 26. I mean, it's not Unicode, so so it does control the space a little bit. It's only it's not even English alphabet. It's Spanish alphabet. So.
10 to the power 120 particles in the known universe.
Okay, so mate.
The universe, which makes Borges' idea.
Yeah.
Impractical. All right. Well, this is a great example of where hardcore computational thinking can give feedback to authors. So say, actually, that sounds like a cool idea, but we've worked it out, and it's impractical. Yeah.
It actually exists because if you pick up a word longer than 400 pages,
Yeah.
I can find the 2 halves. Okay?
Oh yeah.
A dictionary just finds in a dictionary.
Yeah.
If you slice the Bible,
Yeah.
you will find it all in the dictionary.
Yeah. That's true. So, but the trouble is that if you did want to form one of these larger books, you'd have to have some kind of index that told you where to find all the various pieces of it, and that itself, eventually, for a large enough book, wouldn't be able to fit any of those books.
But you would find the index in the library. Or at least the first part.
Yeah. But one of the insights of this that I think is pretty cool is that it shows that the Kolmogorov complexity of the whole can be less than that of parts. So in this particular case, to describe this library, which we'll do in a second kind of in code, it's actually much smaller code than any one of those books, which is something that I found unintuitive. It's probably, I guess, obvious to students of complexity theory. And Borges recognized this, right? So he didn't write it in terms of, okay, look, true, but he showed that somewhere there's a book that contains all the others. Cool. So the code to do this, or to do something similar, I've done using the clean star. So basically you have an alphabet of symbols, and the clean star puts them together in all possible combinations. So the Library of Babel is basically the clean star of ASCII, give or take particular characters. And that's an interesting case because, you know, it's very highly structured, very little complexity. One kind of other example of an artwork that starts to play with the idea of discovery versus invention is Contact. So it's kind of another fictional work, but effectively a message is found within the digits of pi. So again, you know, is that discovery? Is it invention? Is it something in the book itself? The concept is that the universe itself has been altered to place this message within pi, so that somehow the laws of how the universe fits together is something to fit in with pi. It reminded me of something that Phil Wadler wrote in Propositions as Types, which is the idea that the lambda calculus is something to be discovered because of its universality. So natural deduction and lambda calculus should be not only known to aliens throughout our universe, but other universes. So it's some kind of thing that was discovered. That structure is inherent, and we just needed to go through that search space, that very wide search space to find it. So one of my favorite examples of computational musicology is, again, by a musician rather than by someone who studies music, which is called Flutter by the UK dance band Ortega. So in the 90s there was a kind of a moral panic about raves. So people going out into the field, dancing all night to dance music, presumably taking substances the government didn't approve of. And this was something that, you know, the government was very concerned about. So they tried to find a way to legislate these out of existence. And the challenge they came up against, and this is kind of quite a famous piece of legislation, is how to make sure they were legislating against the music they disapproved of, but not legislating against good old, you know, any old concert in the forest of someone doing Morris dancing or folk music or whatever. And so the way they described it, the civil servant who drafted this, talked about music characterized by, quote, a succession of repetitive beats. So in order for it to qualify as a rave and therefore illegal, it had to have a succession of repetitive beats. So the protest that Ortega wrote was a song called Flutter, which, although it's electronic dance music, has no repeated beat. So every particular bar in this song has a unique beat. So it has a really kind of weird effect because it's repetitive in concept but very unrepetitive in realization. Although as they advised on the record sleeve, that if you are going to do this strategy and play Flutter in a field at midnight, make sure you have a lawyer and a musicologist present at all times to confirm that it's not repetitive should the police come knocking.
And then you don't need any substance because of that.
Exactly, yeah. So there's one final example I want to show, which is created by me, which I think might be an example of hopefully where using complexity theory can create something that's a little bit artistically interesting as well, which I call the copyright infringement song. So there was a song called Blurred Lines a while back, which, as well as being kind of horribly misogynistic as well, I got into a bit of trouble with copyright. So Marvin Gaye's song Got to Get It On was alleged to have been the original source of the tune, and in the end courts found that that was true without much expertise in musicology. So what I did was I took a concept much similar to the message in Contact that's encoded in the digits of pi, and took something called the Champenown word, which is a much simpler constant than pi, just created by concatenating the natural numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0, 1, 1, 1, 2. etc. So it's a constant that is like the Library of Babel, a lexicon. It has all other strings inside it. And I designed a very simple decoding scheme. So I guess not that similar to the Gödelization scheme that was used in Beethoven earlier. And so if you then just play this natural constant using this natural encoding scheme, well, to start with, it sounds very boring, right? Or at least weird. So this is just playing a natural constant. Not very artistically interesting, you might argue, unless you're early 20th century composer, I guess. But the observation I found is that, speaking of the universe and exhausting of the universe, that if you looked in that constant far enough, well, you could actually find something that sounds a lot like blurred lines. Right? So this is just playing a constant that's completely natural based on the base 10 system, using a completely neutral encoding system, right? But if you look into it far enough, you find this thing. Well, I did devise the encoding system, but it's nothing special. It has nothing about that particular song, because in fact the key to why it is why it's a copyright infringement song is it does actually contain all other songs of 3 parts, because it eventually cycles through all possible definitions of music. Okay, cool, 5 minutes. So I'll just get to the conclusion. So if the question is, well, computational musicology, what profit? Well, actually, maybe the answer is copyright litigation, right? Because since I've published that song, every subsequent song, I guess, is infringed on, theoretically and in a totally non-legal way, infringed on the copyright of that particular piece of music. And it's true that, I guess, I infringed on the copyright of every previous piece of music before that was generated, but I hope that in the long run that investment will pay off and it'll kind of balance out. But my real conclusion is that applying these concepts of complexity theory and how things are generated and search versus creativity, etc., can actually be an interesting way of not doing just kind of modeling and simulation of music, but actually music criticism, something a lot closer to literary criticism. That you can interpret code in a literary mode, so you can think about not only what it does, but kind of why and how it generates meaning and significance. You know, like Flutter, the song by Otecker. It's based on a computational concept, but it has a real kind of social function of kind of critiquing and satirizing the way that government wanted to control people's musical practice. And I also wanted to show that music and literature can respond to computational ideas. So I'm saying the real profit actually potentially is that if you think about computational musicology as not just a form of kind of scientific endeavor, but a kind of criticism that can engage in a dialogue with actual artistic practice, then that might be a way that we can profit. Thanks very much. Do we have any time for questions, Mike? Sure. Oh, yeah.
Recently I was listening to a musicologist describing incredibly clever models for understanding music. And I was full of ideas and combinators and concepts. And to the question, did you try it? The answer was no, because it was not computational musicology.
Oh, interesting,
Which means that it was incapable of using computer to apply this theory. And I think that's a very good aspect of computational musicology. Ideas can be pushed to facts.
Yes, and that's a very, like, Jerry Sussman in ICFP and his writings about Lisp have that idea. I actually recently, I guess between when this paper was submitted and the present, did a talk on Central African music and modelling that using code. And that was actually a very similar case to what you described, where there's a big book on ethnomusicology, so different music systems. And it was almost stated in a way that was crying out to be automated, but the person clearly didn't have the experience of many people in this room of knowing how to do it.
Doesn't mean that was irrelevant.
No.
That was frustrating.
Yeah, well, and I think, you know, this person could have very much benefited from it. It would have made their examples a lot clearer and they would have conveyed what they meant a lot more precisely. Yeah.
I think there is another use of the concept of complexity. Just relevant to pattern hypothesis. Sometimes when we write synthesizers for artist music and so on, even though there is an infinite many outputs that we can generate, we go bored with it rather quickly.
Yeah.
And I think the explanation for that is that even though, well, the description being quite simple, we as humans are quite good at recognizing these similarities and getting more of it. And that's the thing that's not, I mean, in your code, if you actually use the random function in your code, you can do many different outputs. And some of them might be random, so actually the number of complexity will be very large. Although the description in terms of code will be very small. It's an aspect that at least your code demo doesn't really take it.
Yeah, well, I think one of the things that David Meredith does talk about in his paper, like Analysis by Compression, is the kind of creative friction between our mental models of music and the programming languages model. So he talks about actually kind of an explanation of even subjectively why different people experience the same piece of music differently, as being because we have a base set of musical concepts, and when we hear a song, we're basically learning that song. We're finding a way to fit that into the universe of concepts we already have. So if you have a different set of concepts, so you basically your programming language for expressing that song, if that's different than someone else's, then it might be simple to you because you're used to that kind of music, and it might be complex to someone else because they don't have those primitives. Cool. Yep.
This give a lens on the analysis of one performance that we get in consumers versus listening to Philip Glass his own works versus listening to another performance. It's a very strikingly different experience in a way that I personally am unable to comment.
So the question was, well, does this give you an insight into different performances of the same piece? I can think of a couple of ways. So one of the things I think would be exciting that I haven't looked into is using differential Kolmogorov complexity. So working out how much is this piece different from the other. So what is the complexity of the function required to transform this version into this version, which gives you an objective measure of how different they are. So that's one fundamental way. I guess another superficial way is that even for just music that I've kind of done myself, you can basically apply functions to apply different stylistic ticks to it. So you can take a straight melody and turn it into a swung melody quite easily just with the functional transformation. So if you understood the difference in performance, maybe you could find a way to express that in code so other people could understand it. Have we got
one more?
One more. I think someone from over there might have had their hand up earlier. Yeah.
The thing about the Flutter, you're not
Yes.
You said that no two bars are the same.
Yes.
My expectation for a non-repeating infinite sequence is that it doesn't become eventually periodic. So no Taylor's infinite sequence is equal to any other Taylor, which can still have repeating bars. But still it's never become periodic. And in fact, the sequence of naturals, I forget the name of it. You had.
Oh, the Champernowne constant.
That is also a non-repeating sequence. So
But
that point that leads them to become arrested.
exactly. So I guess the idea of the interaction between repetitiveness and kind of infiniteness. I guess to be a lexicon, to actually have all possible substrings, it's not possible to be periodic because then that would, once you get around to the end of the period, there must be things that aren't contained within that. In the case of Flutter, there is kind of a limit to how many different bars there are, but as the song is only 6 minutes long, they didn't need to actually have an infinite song. They only needed to have enough different bars to kind of keep people going for that one bit. I think I might have run out of time, but I would love to talk to other people about this later.
Thank you, Chris.
Thanks very much.